Welcome to this spiel on distributed convolution kernels. With this 10-minute introduction, I hope to share with you a new way to learn with structured data. If you are here, you already had the opportunity to think about the issue of learning with structured data. In this task, we have structured data on the one side and a class or a number we want to discover on the other. And we want to learn a classifier or a regressor. Defining a convolution kernel is a classical way to go if we want to fully exploit our structured data. Our convolution kernel computes the similarity between two structures with an algorithm. Then, since we use the convolution kernel, we need a kernel machine. We select our favorite and we can now learn our classifier or regressor. I'm assuming here you are familiar with the convolution kernels, but forgive me, I need to give a one-slide introduction to fix some points I need for the rest of the piece. Here on the left, we have the two structures. The algorithm of the convolution kernel sees the first structure as the set of its substructures, and the same for the second structure. Then it performs a weighted count of the common substructures. The genial part of the convolution kernel is that it hides the underlying feature space of the substructures. This feature space is generally huge. You see here a 1 for each active substructure of the two structures and 0 elsewhere. For example, the third substructure of the first structure has a 1 on the first vector, that is, it is active, and 0 on the second. It is not a substructure of the second structure. The kernel is then doing, with an algorithm, an hidden dot product of two huge feature vectors. Then it makes possible what is not feasible. So far, so good. We have the classical ingredients to learn with structured data, and we have a solution to learn our classifiers or regressor. But the power of the convolution kernels is also their limit. If we want to learn with structured data, convolution kernels force us to stay in the class of the kernel machines. We cannot use the linear versions that are faster. We have here a proposal for a novel way of exploring structured data in learning, the distributed convolution kernels. I first use a metaphor to introduce the basic idea, and then I'll try to be more formal. Let's start again from the picture describing the convolution kernels. You should have already noticed that substructures are now colored, the same color for the same substructure. Now, if I rotate the middle substructure, or tree, yes, let's call them trees, it's easier. By the way, after the notation, I believe you still see the same tree. If I rotate the second tree and I put it on the first tree, you should still see two trees. Let's do it with a third tree. Things become a little more confused, but we can still see the three trees. Let's do the same with the second structure. Now, looking at the two small boxes, we can still see in the two images that the two structures have common substructures. For example, we can do a count of the common pixels, and this can approximate somehow the count of the common substructures. In this metaphor, we are showing that it is possible to encode substructures in small regions of the space, and that we can approximate the count of the common substructures. Thus, It is in principle possible to think that we can encode substructures in small vectors, as the images you see in the two boxes. And then, counting common substructures is doing the dot product between these two small vectors. This is the distributed convolution kernel that approximates the initial convolution kernel. The distributed convolution kernels are a new way to attack the problem of learning with structured data. Now, the ingredients are a distributed convolutional kernel that approximates the convolutional kernel we wanted, and we can finally use the linear version of our favorite kernel machine. For example, Pegasus, the SVM learning on the primal space, that is extremely fast. Now, let's see more in details what we exactly expect for these distributed convolution kernels. Let's give names to the substructures and the structure. The structure is Z, and the substructures are C, Cj, Ci, Ck. S of Z is the set of all the substructures that we want to activate in the feature space given the structure Z. What we need are two functions. The first is a gamma function that takes substructures and maps them into the space Rd. For each substructure, we need a vector that is nearly orthonormal with respect to other vectors. Nearly orthonormal means that if two vectors represent the same structure, their dot product is nearly 1. Otherwise, if the two vectors represent two different substructures, their dot product should be nearly 0. The second function is d of z, that takes the structures and produces a vector that represents all the substructures. This is in principle possible by summing up vectors gamma c with a scalar weight omega c on all the substructures in the set S of z. The final vector is in Rd. Going back to the metaphor, the vectors gamma c are kind of representing the rotated colored trees, whereas vector dz represent the figure containing all the subtrees, a sort of sum of the subtrees. Now, giving names to these new old objects. We are defining this new way of representing structures in the tradition of the distributed representation for structures. Vectors derived from functions gamma are the distributed structures. D of z, that represent all the substructures, is the distributed convolution structure. The distributed convolutional kernel between two structures x and y is then the dot product between two distributed structures, dx and dy. In this spiel, I only gave you a rough idea of what a distributed convolution kernels are. There are still many details that are missing to convince you that distributed convolution kernels are possible. First, what are the properties we expect from distributed structures and from distributed convolutional structures if we want to approximate a convolution kernel? Second, we have basically described so far a sort of random indexing of the feature space of the substructures. A real innovation is to define functions gamma that are compositional, that is, they use vectors for some basic structures and then compose these vectors to obtain the vector for the whole structure. Third, we want to obtain the distributed convolutional structures in an efficient way. Leveraging on the compositional definition of distributed structures, it is possible to show that distributed convolution kernels can be obtained with recursive functions. You will find the appropriate pill discussing all these issues. Stay tuned!